Energy system modeling exercise 12. Let's go ahead and open the folder from the Moodle so we can download the template like this. And then I'm going to open up the exercise PDF. So download the exercise 12 template. That's what we did. And use the Markov chain method to generate wind capacity factor profiles in the first sheet of the template, which can be used, for example, in Monte Carlo simulations. So let's go ahead and try and do that. So why we can utilize this Markov chain in here is that we can first determine different states for these capacity factors. And the previous state is always going to, or rather the second or the next stage or the state is going to always be dependent on the previous state. So what I mean by that is we can first make these kinds of, let's call them bins. And I'm going to determine the minimum and the maximum and delta capacity factor in here. So let's call minimum is going to be this one and maximum is going to be these ones, and this is going to be maximum minus minimum divided with 9 since we have 10 bins. So let's take the minimum in here and sum up the previous plus the delta capacity. And this is going to have to be dollared like this. So we have these certain bins in here. And now what we can do is we can match those uh, numbers, what we have of the capacity factor in here to those certain bins. And as we are doing this in Excel, it is a bit difficult to do. And I noticed that if I just use this match function, so I could see that I say match lookup value would be this, lookup array would be this. And then the question is what kind of a match type is it? Is it going to be less than or greater than if we put this one? You can see it doesn't always offer the solution. So I made a workaround for this. Doesn't seem to be working here at all. So let's try this one. So now it gives us something. But I think in all of the cases, this is not going to work. We can actually see, yeah, it doesn't go to this number 10, 10 at all. So what I did in here is instead of using this match function for those uh, plain numbers, what I have in here is I can substitute this one like this. So what I have in here is absolute number of these ones minus these ones. So if I'm going to do it in here to show you, it's going to be this one minus this one. So that's going to stay constant. It's going to look something like this. And now if I take the absolute value of that, so let's take abs like this, you can see that it pinpoints the closest value to it. So this would be, in fact, this bin number 7, I presume. or we'll see. So this would be utilized to calculate the uh, value that we are after. So the one that is the closest to us. So this just putting this wind capacity is not in. It's not enough. So we have to have this first off uh, these ones. Sorry, these ones minus this one. From that, we're going to have to take the absolute value. And since this is going to return an array, then I'm going to take the minimum value. So it's going to just give me the minimum value like this in here. So there's the absolute and like that. And then what I'm going to match it with is this one, like here. So it's going to find the corresponding value. And if I put 0 in here, let's see, something is missing parentheses or having too much of them. Yeah, like that. And now that one doesn't seem to be right. So let's check what's the matter in here. So I'm finding the minimum value. Uh, in here. Yeah, we have to have the absolute of these ones. And the same goes in here. Absolute of these ones. Yeah. So now, as you can see, it goes to this bin number 8. And let's lock these ones down. So like this. And now I have assigned a bin. So to say a state for this wind capacity factor. So for example, in here it's 7, rather 8, here it's 7 and so forth. And if I were to draw this uh, in a way that I'm going to put a couple of zeros, so it's going to go till the end, you can see that it fluctuates between 1 and 10. So all of these states are now occupied. And what you can see is this kind of resembles the capacity factor. If I were to plot this one, there is a bit more variation since these are discrete numbers. So however many bins you have, the more accuracy you will get. But what does this have to do with the Markov chain? Is now when we assign the next number right next to here, so this is the current number and this is the next number, we can see that there is a pattern in here that this go 8 changes to 7, 4 changes to 5, 10 stays in 10, 9 stays in 9. There's never a too big of a jump. So these kinds of drastic jumps can be excluded with this. So actually what we can do is we can determine the uh, kind of changes in the states. So let's make 10 states in here like this, 10 states. And from here, we can calculate whether number 1 changes to number 1 or rather remains in number 1 or number 1 changes to number 2. So what we can use for that is this count ifs function. So I can say count ifs and count ifs, not count if. So the criteria range is going to be this one. So first we're going to check whether this is number 1. So this is remaining same all the time. And then I have whether the number in question, it goes these ones through. So whether this one or whether the number in question is number one. And this can move downwards, but it cannot move sideways. So it can move downwards, but not sideways. And the other one from here, I'm going to copy this one. And this number is going to be this. And let's now change the wrong one. So like this. So first you go through these ones, and then you go through these ones. What you could have done is just put them like this. But for the sake of clarity, I'm going to use two of these columns like this. So then we're going to check if this is 8, or rather 1, if it's going to be still 1. And this can move sideways but not downwards. Sideways but not downwards. And if we do it like this, you can see it forms this kind of a diagonal matrix. Everything else is zero on these kind of outer rims, edges, but on the center line, you can see number 3, or rather state number 3, can change in some cases to 2. It remains in many times as 3, and it can change to 4. It can even change to 5 in few occasions, but it doesn't change to 6, 7, or 8, or so forth. So this gives us the probability on how probable it is for state number 6 to change to 5, to change to 7, to 8, and so forth. So there, for example, are no instances that number 6 state would change to 1. So this kind of eliminates the kind of random fluctuation in this capacity factor. So where you be doing, if you were doing these kinds of Monte Carlo simulations, you don't want just random numbers for your wind capacity factor. So this Markov chain enables you to generate at will a lot of these different kinds of wind capacity factor profiles, but in a way that it resembles the actual phenomenon. So let's sum all of these together in here. So then we can calculate the probabilities. So I'm going to copy this one like this. So the states are followed in here. So this one divided with this one, and this can move downwards, but not sideways. So here and here. And all of these rows have to be a sum of, the sum of them has to be 1. So you can see it's just integers in this sum when I go downwards. So this is 1, this is 1, this is 1, 1, 1, and so forth. And then what we have to do is we have to make a cumulative matrix out of this one. So this is the Markov transfer matrix. So I'm going to have this one in the first row, but then I'm going to start accumulating these ones. So the previous plus the current one to here and to here. So you can see instead of zeros, we have ones in here. So now when we want to generate the random Markov chain based capacity factors, we have to have a random number. So first we're going to say equals random in here, rand. So it generates us random numbers. And the first one we can actually exclude since I want to start from state. So this is going to be the random, and this is going to be the state. And then we're going to go back to the capacity factor, so CF capacity factor. And now this is the kind of trickiest part in here, and this was really hard to kind of formulate in Excel how to do this. So what we want to do is we want to, based on this state and this random number, state is 5, so I go 1, 2, 3, 4, fifth state. I gather these numbers, and after that, I try to see this random number in here, 0.61, at which point this kind of condition is met. Not in here, not in here, not in here, not in here, but in here, it's met. So number 5, when we have this random probability in here, we're going to utilize this transfer matrix and see it's going to turn out to be state number 5. If this were 0.2 or 0.1 rather, then it would fall to this state number 4. If it was 6, then it would fall in here, and 7 after this 0.99904. After that, the random number would always guide it to this number 7, not number 8, 9, or 10, but number 7. And that's what we are trying to kind of generate here in Excel. And this was a really tricky thing to do. So I would recommend in here to utilize maybe Python with some AI. So first off, we want to fetch for us the right row in here. So let's start building it from there. So let's get the right row. So what I want is I want offset. The reference cell is going to be this one. So 1, 2, 3, 4, and so forth. So that's always going to remain constant. How many rows do I want to go downwards? That's the previous state, and that's going to go onwards with us. And then what we need is how many columns do we need to move? 0. What's the height of the wanted matrix? It's going to be 1, and the width is going to be 10, since we have 10 bins in here. So that's what I'm going to state, that it's going to be constant. So now it's actually going to spill it in there, so I'll show it in here. So it's going to find this one. And we want the same thing as with the state definition. We want to have the subtraction in there. So let's see. This is the one we want to subtract from it. So this one minus this random number. So that's going to give us the curve again, the kind of 0 point in here is going to indicate the right spot. So, and we want to see which one of those are above 0. So I can have an if statement in here. So if this one is going to be above 0, then I'm going to return the same value. Otherwise, it's going to be false. So let's see what comes out of there. Yeah. So these ones. So now the random number is referring to this one, and the first value that is going to be, now it's 0.26. So the first value that is going to realize the condition, this isn't the value, but it's first, second, third, fourth, fifth one. So in here, it would be not the fourth, but the fifth one. So that would be kind of meeting the condition. And we want to have the minimum of this one. So let's take the minimum out of here. So that is the, I can put this one, for example, to 0.1. So now we'll see that it's going to be all the time 0.067. So it would correspond to this value. So this minus 0.1 is this one. Okay, so then we have to match it. So we're going to have to match this number that we got from here to this offset minus this one. And since they are always positive, we're going to say abs this number. And otherwise, or not otherwise, this is not an if statement anymore, but this states that it has to be an exact match in here. So now we got state 4. And if we go on to 0.2, it would be this fifth and 0. Let's put 95, then it would go up to 6. So now we have a function collection that determines the next state. And let's see if it works. If I were to plot this one, so insert, and we're going to plot this one, the states move between 1 and 10, as they should. So now it's only a matter of determining backwards the capacity factor based on that. So we can use the index function. So the index function needs the array. Actually, we can delete this one so that it doesn't bother anybody. So index array is going to be this one, and that's going to stay as constant. This is going to be column number, and rather the row number and the column number, I'm guessing it's going to be 1. Yeah. So now we have the capacity factor in here. Yeah, and that fluctuates between close to, let's see, it goes down to 0. Yeah, but this is really close to, so the minimum value in here, it's really close to 0. And it doesn't go above this 92 as it shouldn't, or rather as it didn't in the original data. And now what we can do also, this is kind of hard, we can make two lines in here. The other one shows the original capacity factor as blue, and this is the new one. So whenever I hit enter here, you can see, hopefully, that the capacity factor changes based on the Markov probability. But even though it changes, we can see from here load duration factor, or let's say load duration data, and a load duration Markov. So I'm going to have equals large. So the array for the original data is going to be this one. That's going to stay constant all the time. It's going to be 1. And the other one in here, I have to put this one to 1. And this is the Markov-based capacity factor. And now if the original is going to be moved into this data, and this is going to be moved to this Markov-based model, then you can see there are these discrete bins. So if you increase the bin number, then you get more resolution. But whenever I press the enter and the random numbers change in here, then we're going to have more of these different load to, or the rather capacity factor time series, but they don't behave erratically. They behave in a similar manner as the original wind capacity factor. So with that, you can make these Monte Carlo simulations. Another kind of application that we could utilize this for is in here, as in this course Moodle assignment 4, you are to examine the changes in this kind of a share of these energy production types. So we have different assets: nuclear, coal, gas, and wind. And year 1 is going to give us 100% share of this coal. And this is the Markov transition matrix that we can utilize in here, and we're going to use it in a deterministic manner. So this is year 1, sorry, year 0. So that's 0. This is going to be 1, not 10, but rather 1. And let's see if it works like this. Yes. So we get 10 years from there on out. And how you can do it is just matrix multiplication, these ones and these ones. In here, we're not using any stochastic elements, so this is completely deterministic, and this is going to stay as constant. So I'm going to lock down those. And now if I drag it to the right, and we can see the shares. Let's see if it goes like this. And we'll take these ones out. And also change the year from here. So edit this one, and rather starting from 0, it's going to start, rather than starting from 1, it's going to start from 0. So this is year 0, 100% coal. And we can actually make it in a way that that would be 0.2%, or the 0.2 share of gas and 0.8 share of this coal. And this shows us how the system changes. So if I increase the wind in here and decrease the coal, you can see how the system converges. But this doesn't have any kind of a stochastic element, so that's what we're going to add now. So this is the deterministic way of using it. But now we want to have randomness in there. So we want to see how this random fluctuations, randomness in the system changes the behavior. So let's again assign these states in here. So I'm going to have states from 1 to 5, since we have 5 different assets. And now you can see that this, what it means is nuclear stays as nuclear with 80% probability. It changes to coal with 10% probability, and so forth. So now we're going to take the cumulative matrix. As you can see that not even a single one of these probabilities has to be 0. So this was related to this wind behavior. It doesn't have to be so. And these would be somewhat hard to determine. I'm going to show in this Markov fit how to determine them. So let's put still the cumulative values first. So summing up these ones to the previous ones like that. And now we need the random factor. And I'm going to make it in a way that I'm going to have 100 simulations. That would be an easier way, or rather smarter way to do this. But let's do this drag and drop style version of generating 100 numbers in there. And then I want 10-year simulation. Let's make it in that way. And I'm going to say random numbers between 1 and 0. So this is going to be that like this, and it goes to I'm going to just delete the rest if there's too much. Yeah, so let's take these ones out. Now we have random numbers, and let's initialize the simulation. So year 0 is going to be in here. This is going to be the years, what the random number related to that is. And now we're going to calculate what are the stages in here. So year 0, if we are to say that everything is cold, 100% is cold, that is state number 2. So we can say this is state number 2. And then we'll have to start doing the simulation year by year, like this. And now we can utilize the same function as in here. We're just going to have to be mindful of what everything is. So this one is the offset. Let's see, from here. So all of these cells have to refer to this before the probability matrix in here. And this was, I assume it was the number 5, since we had the 5 states only in here. This one is going to be the probability. So probability goes into here, and then this is the previous state. So based on the previous state, we can determine a previous state and also the probabilities. We can determine what is going to be the next state. And now you can see there's only single numbers in here. So coal remains as coal, remains as coal, remains as, well, then it turns to gas. Yeah. And the gas remains as gas until that turns to wind. And now if we run the simulations multiple times, we can count these numbers. So if I'm going to have these ones still in here, we're going to have a count if equals count if. The range is going to be this one, so let's not take the year number in there. And that can change sideways, but not go downwards, because we're going to drag this. This can change sideways, but not go downwards. And what are we trying to get from there? We are trying to get the first state or the second state. So this can move downwards, but not sideways. Move downwards, but not sideways. So let's count those. There should be 100 of coals. Yeah, that's what it is. And now, since we have 100 of these simulations, we can just say 100 in here. A better way would be having, for example, maximum from here on out, and let's put a couple of zeros in there. So it's not going to change. And by the way, I'm going to put these ones into dollars. It doesn't make any difference, but for the sake of being consistent. And now let's just drag these here. And we can see, inserting the 2D line, that there is a stochastic element in here. And what it does, it changes, makes some fluctuation in there. And now again, if I change the random numbers, it's going to change these ones. There is a certain probability in here, but then if you have a limited amount of simulations, then it makes this stochastic nature in there. If I only had 10 simulations in there, it would have been a bit more noisy. So we're generating kind of noise in here. So compared to this really deterministic Markov chain, this utilizes the random numbers in here. So where on earth to get these numbers? Is, for example, you go to Ensoi and download, there should be year, not from 0 to 2 jump, but like this. So this is the initial state in here. And these are, I believe, from, I'm not even sure which year was it, but I think it was 2016 onwards that I took these ones. Yeah, there's the molecular the jump. So this is nuclear. So it must have been somewhere around 2016. So this is our baseline. And what happened then is, you can see from here, there's the wind, there's the nuclear, there's gas, there's coal, and there's solar. So let's calculate the proportions of these. I'm going to have a sum of all of the rows, like this. And then we're going to determine the Markov chain transition matrix. So the probability is based on these ones. So let's take first, and as in the Moodle exercise, so this can move sideways, but not downwards. Sideways, but not downwards. Or rather, vice versa. It can move downwards, but not sideways. So downwards, not sideways. Let's see if it went right, like this one. So as in the model exercise 5, we're going to use these proportions rather than the absolute values. So if I'm going to change this one into here, it's going to give us the proportions of different production assets. And then this is one way of doing it. For each case, it's not the right way of doing it, but let's have the change of beginning and end. So what you have in here is you have the total or the total difference between year 8 and year 0. So how much the proportion has been changing. And actually, in here, we want to calculate how many of these, let's have these sum if. So let's sum if it is below 0. So these are the downs. And the other one is the ups. And this is vice versa, well, vice versa like that. So now what we want to do is we want to determine how to allocate these one. Nuclear has lost some of its share, and wind has gained. Coal has lost, solar has gained. So if coal loses some, which proportion does wind and solar take? So let's take these ones in here. I'm going to make maybe take a transpose out of this one as well in here. It's easier to formulate. And then I'm going to have equals these ones. And in here, I'm going to have transpose of this one. Like that. And now comes the hard part. How to determine this one is I'm going to see if this is being a down and this is being up. So if that would be the case, if nuclear, let's say nuclear is down and wind is up. So these ones are going to be 0 now. And how big of a proportion does wind get from nuclear? So let's start formulating the if statement in here. So we're going to have to see if, and there's going to be two conditions. And if this one that can move downwards but not sideways, it can move downwards but not sideways, is below 0. And if this one is that can move sideways but not downwards, if that is above 0, that would mean that nuclear would give some of its share to nuclear. Well, actually, it gives to nuclear, but we're going to have to deal with that later. So if it were to this wind, for example, if this was positive in here, then we can see what happens is we want to give this, so can move downwards but not sideways, and divide it with the downs. So how big of a proportion of the downers it's going to give, so multiplied to the uppers. So this one can move sideways but not downwards times this one. And let's put that, well, I'm guessing it doesn't have to be put in parentheses. Yeah, like that. And otherwise it's going to be 0. So let's see if we get anything meaningful in here. Everything 0 as it should be, except in these cases. So nuclear has some kind of a probability of turning into wind and turning into solar, because those are the ones that rise, and all of the else are going downwards. And actually, in here, what we need to do is we need to, since we have 1, 2, 3, 4, 5, 6, 7, 8 years. So let's divide with 8 all of these ones. So that is going to represent the yearly change, because that's what we're after, not the overall change. So that's the yearly change. And then something is still missing from here. And what is missing is that nuclear should also be able to retain its share. So everything else, this is 1.2%. The rest has to go to nuclear. So that's something that we have to take into consideration. And there would be kind of an automated way of doing it. But for the sake of not using too much time in here, you can determine that also by yourself. But an easy way, kind of manual way to do it is just say this diagonal elements in here, 1 minus everything else. So, and actually I can say that it's just going to be wind. Well, for the sake of being general, let's do it like this. If I'm going to change something. So that's going to have everything else 1 minus this, 1 minus this, 1 minus this one, and this one, and the same goes for here. And since there are no other things in here, this would be 1. But for the sake of, if we want to say change something, I'm just going to do it like this as well. So equals 1 minus. So now we have the transition matrix in here. Nuclear is going to stay as nuclear in 98% of the cases, and 1% goes to wind, and 0.01% goes to solar. So solar isn't too much of a riser in here. And this is the transition matrix then that we can utilize with this stochastic Markov. So actually what I can do is I can take a copy out of this one. So move to the end and create a copy. Like that. And let's copy and paste this matrix from here to here. Like this. And I took a bit too much from there. So let's go backwards and take only the matrix like this. And copy and paste it there. So our states are still in here. Okay, what next? We need to determine the initial stage. And how you can do that is they are actually in here. So if we take round this number times 100 0 digits, we're going to see if we have 100 simulations, we need these ones. So let's take these and move it to here, and maybe make a transpose of those ones. I have to paste special since I want values and transpose like this. So this is the initial kind of state that we have to have. And unfortunately, I wasn't able to kind of find a better way to do this. There is a way, but it's a bit laborious if we want to automate it. But we can make it like this. So the first nuclear, we want 31% of nuclear. Since we have 100 simulations in here, I'm just going to say everything is number 1. 32 of, so 31 of these. So there's the count. So I'm going to have 32 of rather 31 of these is one. So let's put two after that one. And we need 32 number twos. 32 is there, and the next one is going to be three, and multiply that till the end. And how many threes? We need 20 threes. So 20 is there. There's the count. And this one is going to be number four until the end. We have 17. No, I missed one of those, but it's pretty close to the original one. So let's make it. Uh, Actually, yeah, we're missing something since this isn't actually 100. So that's what we corrected. We allocated one more to the wind. Yeah, so the rounding up and the of the digits uh, made one asset disappear, but we allocated that to the wind now. So let's be fine with that. Okay, so this is now, since we already had the kind of template, what's going to happen in here. Now it's presented in here. So I'll try to take the shares of these ones. So let's take these ones. These are the shares. And let's move them into here as a values and transpose. So now we have 8 years. So not 10 years. We're going to have to remove a couple of these ones. Or actually, we can leave it be and let it be the future simulation of that. So if I were to utilize this as a base and move it in here, then this is the original what happened, or the actual, and this is the simulation. And now again, if I rather change the random values, I'll see what kind of changes do I have in the outcome. And of course, this has to have a finite amount of those simulations to be able to generate this randomness in there. But as you can see, the simulation results in this case, when we have 100 simulations, they can be rather different since there are 5 of these assets. So there's a lot of these different combinations that can happen with this stochastic nature of the simulation. And in the Moodle exercise 4, you are to assess a certain kind of effect of policy into, for example, how big of a proportion of this coal would be turning into wind or solar more than in this baseline scenario. And remember, the baseline scenario was calculated based on the kind of average. So, well, it's average since we have the overall change, and in here it's been divided with 8. So how many changes occur in here? So that is the average change, but it doesn't mean that we are going to get these discrete changes or the rather abrupt changes as in here, where the Olkiluoto 3 got online. But yeah, there is the exercise 12. So this was to learn how to utilize this Markov chain with different applications. So we had the wind, and then we had the energy system or the energy production asset shares. How do they develop? And remember, not every methodology is good for every application. So in the Moodle assignment 4, you are also having to assess, is this a good methodology for this kind of a case.